Hello there. In this lesson, we're going to learn about ionic compounds. So ionic compounds clearly contain ions. Hopefully you've heard of them before. This is an example of one here that you might have around your house. This is a Himalayan salt lamp. It's the same salt that's in table salt, sodium chloride, but it has some extra minerals in it that give it that nice pink color. You can buy it to put on your food as well. Now it's mined way over in the Himalayas in Pakistan, I believe. And here's a little image of one of the places where it's mined out of the earth. So they basically dig it out. This used to be a seabed like millions of years ago, and then the water all evaporated and left behind this nice layer of salt, and people are digging it out and selling it all over the world. So let's learn a little bit more about ionic compounds. Here's a few more examples from around your house. Of course, table salt, the classic example of an ionic compound. Baking soda as well is an ionic compound, just ground a little more fine. Epsom salts or bath salts are also ionic compounds. There's the name right there, magnesium sulfate. And sometimes the salts will be dissolved in water. This one is sodium hypochlorite, and dissolved in water it gives you bleach or Javex. It's like a brand name. Yeah, so they're all around, and we're going to look at some of their properties. So as far as properties go, if you look at table salt closely, even with your naked eye, you'll notice that it has sort of a cubic shape, and it'll be hard if you roll it between your fingers. And this is sort of typical of ionic compounds. They all have little crystalline shapes, maybe not always cubes, but some crystalline shape, and they're very hard. Now some of them will dissolve in water. So if you take those same crystals and throw them into some water, they'll dissolve. And those ions, once they're in the water, they're free to move. And that allows for electricity to transfer from one place to another. So as a solid, they won't conduct at all, but if you throw them in water, they will. Pure water doesn't have any ions in it, and it won't conduct electricity. The water that comes out of your tap probably will, because there will be ions in there. That can allow the electric charge to transfer from one place to another. So that nice regular crystalline shape that you get, like with the table salt, is the result of a repeating pattern of ions that every ionic compound will make as a solid. And so that's called a lattice. So a lattice is visualized here as a repeating pattern of oppositely charged ions, right? So in the case of the sodium chloride, it'd be a sodium ion, and then a chlorine ion, and then another sodium ion, another chlorine ion, and that's going to repeat in 3 dimensions to give you that lattice structure. The formula comes from sort of the smallest ratio of those ions. So with sodium chloride, it's pretty simple. You just take one of each because that's the ratio. Now, you probably never ever have a single sodium with a single chlorine. It'll always be, kajillions of them together to make that crystal. So that's why the formula really only represents the ratio, not an actual unit of ions stuck together. So to find that formula, hopefully you remember the good old crisscross method, which is a way to find that lowest ratio of ions. What you do is you work out the charge of the elements that are in the ionic compound. Here's sodium. We see sodium here, which we know is a +1 area, so it's got the positive charge there. And then oxygen's over here. We know that it's in the -2 column here, so we put oxygen with -2. And then what you want to do is crisscross those values, not the positive and negative parts, but the numbers. And you can leave out the ones. If you write the element at all, that means there's one of them. And so what you'll end up with is Na with the 2 and O with the invisible 1. So the formula, the ratio of ions, can always be determined from the charge that you can get off your periodic table. So here's a few more to try. We got sodium again, which we know is +1, nitrogen, which is -3, magnesium, which is +2, oxygen, which is -2, aluminum, which is +3, sulfur, which is also -2. And then we can do our crisscross to quickly work out the formula. So we got Na with the 3 and N, like that. With magnesium oxide, you might do this to start with, Mg2O2. But since it's a ratio, you want the lowest ratio, so you can reduce that down to just MgO. So that'd be the proper formula there. And the last one here, we're going to have aluminum. I'm going to need 2 of those for every 3 sulfurs, because we would do our crisscross with those values there. Great. So naming binary ionic compounds is pretty simple as well. Binary just means 2 elements. So as long as there's 2 elements, you're going to follow this basic rule. For the first word in the name, you're just going to name the first element, usually a metal. So you're going to say sodium. And then for the second one, you're going to change the ending to IDE, right? So instead of nitrogen, it's nitride. And for the second one, it's going to be magnesium. Instead of oxygen, it's going to be oxide. The last one here is aluminum. And then instead of sulfur, it's going to be sulfide. Right, so IDE on the end. IDE just means that it's a binary compound with 2 elements. All right, so our added complication this year is that some of those elements have more than one possible ionic charge. And so we need a method in our name to communicate which of the charged ions we're using. And so the first method is called the traditional method, and it uses suffixes. And so if it's the lower of the charges, we're going to put an OUS on the end. And if it's the higher one, we're going to put IC, or an ic sound at the end. The other thing is that there's a handful of the elements that use their Latin names, and so we're just going to learn 4 of them. So iron is ferrum, so if you're going to use the lower one, that's going to be ferrous, and if you're going to use the higher one, it's going to be ferric. And for copper, it's going to be cuprous, and if you use the higher one, it's going to be cupric. And for tin, the Latin is stannum, so it's stannus. And the higher one is going to be stannic. And the last one here is lead. The Latin for lead is plumbum, so replace the bum with us or ic, so plumbus or plumbic. So let's look at a couple examples. So a compound here, we've got iron. It's got the 2 charge, which is the lower of the 2. So if we put that together with oxygen, oxygen of course has the negative 2 charge, and so that means just 1 of each. So that would be the compound with iron with a 2 charge, and so the name would be the lower one here, and you're going to call it ferrous oxide. Now if we use the higher one here, you're going to end up with a different compound. Going with oxygen, it's going to be Fe with the 2 and the O with the 3. After you do your little crisscross. And so since that's the higher charge, we're going to call this one ferric oxide. Then we're going to look at these last 2 here with copper. We got a lower and a higher, so we're going to use cuprous and cupric. With the lower one, the charge on the oxygen is 2. It's going to be like that. With the higher one, they're going to even out. We're going to have 1 of each. So this is going to be cuprous oxide. And the last one would be cupric oxide. It takes a little practice, but you'll get the hang of it. Now, thankfully, there's a little simpler method that has been taken up in recent times, and it's called the IUPAC method. IUPAC stands for International Union of Pure and Applied Chemistry. And so it's the standard way to name things now. It's the most common way. And if you're going to learn one way to name your compounds, this is the way to do it. Now, same compounds, right? You can have the same set of elements being stuck together. I'll put them back down here. Don't have to go back through that again. And if you want to name it this time, you're going to use Roman numerals. You're going to use the English name, so you're going to use Roman numerals for the charge of the ions. You only need to put the charge in for the ones that are multivalent. So if you have like potassium or calcium or things that only have 1 charge, you're going to not bother with this. Now, as far as the numbers go, we've got 1, 2, 3, 4, 5 is really all we need. Maybe we can do 6 as well. And the Roman numerals for that is like I. You can put the top and the bottom on the I if you want. II for 2, I for 3, IV for 4, V for 5, and VI for 6. And that's pretty much as high as I've ever seen in an ionic compound. So this one here has a charge of 2, and so you would say iron, and you'd put the 2 down there for oxide, right? Iron 2 oxide. This one has a charge of 3, so it'd be iron I 3 oxide. So it's a little simpler. I need copper for this guy, copper 1 oxide, and this one has a charge of 2, copper 2 oxide. The biggest thing that students sometimes gets mixed up with at the beginning is they might look at the number here in the formula and use that for the number in the name, but you shouldn't do that because the number is supposed to represent the charge, not the quantity. Don't do quantity, yes, do charge. Alrighty, so let's do a few more together just to finish this off. There's good old barium. It only has 1 charge, so we don't have to bother with any of this naming stuff. And we can just call this barium chloride. Right? We got cupric chloride, so that's our copper. And since it's ic, we're going to do the higher one, so that's copper 2. So that'll be CuCl2, very similar to the one above. Next, we have FeS. So there's 1 Fe with 1 S. And we know that sulfur has a -2 charge. So in order to balance that out, that means the iron has to also have a 2 charge in the opposite direction, so +2. So that means it is going to be the iron 2 sulfide. Sometimes you have to do a little deduction to get the charge. Here we have tin 4 oxide. So tin is over here, Sn, and we're using the 4 one. So we got Sn is 4 plus, and oxygen is 2 minus. So if we do our crisscross for that, we'll end up with Sn 2O4. But that can be reduced. So our final answer is going to be SnO2. Yay! The last one here is nickel and 3 bromines. So you look for your nickel. There's the nickel there. And we've got 3 bromines attached to it. So that means we must be using this nickel 3 ion. So you can say nickel 1, 2, 3 bromide. Great. Hope you get some practice with that. I'll see you soon.